Hi class, welcome to section 5.8. So the last two sections in this chapter, we've done all the applications to integrals. So we're done with that. What we want to do for the last two sections is be able to integrate more complicated functions. So we kept it pretty simple so far. So we're going to add on integration by substitution and integration by parts in the next section. Now, the integration by substitution is simply the backwards process to the chain rule. Okay, so it's the backwards process to the chain rule. So it will allow us, as I said, to take derivatives of more complicated functions. So let's see what the chain rule was. So the chain rule was about the composition of two functions, yes? Now, if I want to take these two functions and find the derivative of that, now what's going to be the derivative of a composition of two functions? The rule said is that you're going to take the derivative of the first function, leave the inside function alone, times, move on and take the derivative of the inside function. Now, just the same, yes? What we wanted, as we did with what? Just the same as we did with all the, here's a function, I'm taking its derivative, yes? Now what do? I'm giving you the derivative, yes? And I want to find the function itself. So I'm taking the antiderivative of the derivative and I'm getting the initial function back. So what we are going to start with is this part. Now this part seems to be a little bit complicated, but that's how we would recognize that we're in the backwards process of a chain rule. The chain rule gives you the product between two functions, yes? The outside function at the inside function times the derivative of the inside function. So every time we're going to go backwards, we would have to see something like this. So taking the integral back, that's what we're going to see. We're going to see the integral of something like this, yes? And then what are we going to come up with out of this? Derivative, antiderivative, cancel out, and I'm going to come up with this composition of two functions, right? So in other words, this f of g of x is what's going to be my answer, right? So that's what I'm going to come up with, a composition of two functions, given that I am starting with its derivative and being asked to find its antiderivative, right? So the original function back. So in order to, I'm going to write this down, in order to use integration by substitution, so this method is the backwards process to the chain rule, right? So this method is the backwards process to the chain rule. So we'll recognize this integration by substitution if, so in order to use integration by substitution, we must have inside the integral. So what does the inside of the integral what does it have to look like? A product, right? So inside that integral, you must see the product of a composition of two functions. You must see the product. You must see the product, yes, of what? The composition of two functions, that's this part here, yes? You must see the product of the composition of two functions, that's that part, and what else? And the derivative, yes, the derivative of who? The inside function. That's when you know you got yourself the chain rule backwards. So, and then what else do you have to see? The derivative of the inside function. That's this part. Okay, I don't want to quite highlight it because it might just color over and you can't see it to read it. So what I want to do is I want to give you some integrals and you will look at them and you will tell me, will we use the substitution, the integration by substitution for it or not? Here it is. What if I'm asking you to find this integral? Definite or indefinite, it doesn't matter. 6x squared minus 7x plus 5 to the power of 10 times 12x minus 7. Are we going to use the substitution rule for this or not? Well, I see the product. I see a composition of two functions. Do I also have the derivative of that inside function? Is this the derivative of the inside function? 12x minus 7? Yes, it is. So yes to substitution rule. What about this? Integral of the square root of 4x to the third minus 7x squared plus 9x times 2x plus 1. Will I be using the substitution rule or not? Well, I see a composition of two functions, right? That's this polynomial to the power of 1/2 times. Is this the derivative of this inside function? In no way possible. So that's not going to be a substitute. I can't figure this out. It's going to be maybe other methods. As a matter of fact, very few integrals can be. I mean, this you could find derivatives of pretty much everything because of the rules, but going backwards with a complicated function like this, it's really insane. So yeah, we probably can't even find this antiderivative period. So in other words, there might not be any functions in this world whose derivative is that. No problem. Let me give you one more. What about this? The integral, let's put in an exponential function. Those are there too. Okay, so is this a composition of two functions? Yes, it's an exponential function with another polynomial as the exponent. Is it a product? Definitely. Do you see, is this factor the derivative of the inside function of it? 6x? Absolutely. There it is. Yes, we will use the substitution rule on this. Okay, so that's how we'll recognize it. What method, right? Here are a bunch of integrals. Go find yourself the antiderivative. What method are you going to use, right? Well, if they look pretty simple, obviously, hopefully, whatever we've done so far. But if it starts to look complicated, it doesn't mean they all work with the substitution, with integration by substitution. Remember, there's one more section coming up. Maybe it's that. Again, that would be called integration by parts. So we'll see how that works. Okay, so let's find the antiderivatives of these two functions. We said we can use the substitution rule on, and let's see how that works. So find the antiderivative or the definite integral. Either way, same two names. Okay, all right. The first one, integral of 6x squared minus 7x plus 5 to the power of 10 times 12x minus 7 dx. Okay, so it's called also U-substitution, or the integration by substitution, for a reason, and that's because we will substitute something. What am I going to substitute? So remember how I said it's important for you to recognize that there's an inside function? We're going to call the inside function, whose derivative, by the way, I also see. The inside function, whose derivative I see, we'll call that a u. Okay, so steps. Number one, call or substitute the inside function and I'm going to put in parentheses, whose derivative you also must see right? So do we see here the derivative of 6x squared minus 7x? The derivative would be 12x minus 7. Yes, that's the other factor, right? By u. Okay, so that's what we call the U-substitution part. Okay, so we'll call that by a u. Okay, well, let's do that. So let u equal to 6x squared minus 7x plus 5. Okay. All right, so what are we going to do next is take its derivative. Take the derivative, its derivative. So what do I mean by its? The derivative of u, this u guy. With respect to x. So I'm going to use Leibniz notation. So rather than writing a u prime, you'll see why. Rather than writing y prime, by the way, it is y prime, yes? But also in Leibniz notation, it's called du dx, right? So what's the derivative of this u? It's equaling to what? 12x squared minus, not 12x squared, 12x minus 7, yes? Well, fine, I took its derivative, now what? Well, watch this. This is a ratio, and that's why we like this Leibniz notation, because it's the change in u with respect, or the change in the function with respect to the change in x, which is a ratio, right? It's a rate of change. That's what it is. It's a ratio. Change in the function values divided by the change in the x value. So what I'm going to do is I'm going to multiply both sides by this dx. And I'm going to bring it over. Now, why did I use Leibniz notation? Did you see a dx in your problem? Yeah, that's the change in the x. That's really the width of those intervals and those area ideas, right? When we talked about the areas, that's where the dx comes from. So now what we're going to do next is substitute all the parts, substitute back. So substitute all parts of the integral in terms of u now. So let's see how that might work. So substitute all parts in the integral in terms of u. So this was the integral I had to find. So I'm going to rewrite. I have the integral of, so I have to go back and forth, but there it is. I see 6x squared minus 7x plus 5. What did we call this whole thing? This whole thing was called a u, so I'm going to write u in its place. Okay, what else did it have? It had a parentheses and a 10 exponent on top of it. So that whole polynomial quadratic was called u, so I'm going to do that. What's the second part that you see here? You see 12x minus 7 dx, but what does 12x minus 7 dx equals to? That just equals to du. Now look at that. So once you have the substitution, you should not see x's and u's combined. It should be one variable only, and that new variable is your u. So this is it. Once I substitute it all with this new name, that's what it turned into. Du was the derivative of u with respect to x, which is exactly that part there. So this is easy now. What do I do next? Find the antiderivative, yes? This is something I can easily do. So now find the antiderivative. This should be easy now. I'm going to put this in parentheses. This should be easy now. Easy to do. And again, this is why there shouldn't be no x's and u's combined, because then you don't know what to do. It's a derivative with respect to u. is an antiderivative, I should say. It's an antiderivative with respect to u. U is the name of your variable. Yeah, there it is. There's my variable. So what's the integral of u to the 10 du? Well, that's u to the 11 over 11 plus, don't forget, it's a constant now because it's just an indefinite integral. It's just a function. Okay, so what do I do next? Well, my story was about x's and not about u's. We just used the substitution to make it easier for us to find. So what do I do back? I resubstitute u with the expression of x. So put it all back in terms of x's. So this is my answer, right? I found the integral, right? So what is my answer? Instead of u, what do I write? What was u? It was 6x squared minus 7x plus 5 to the power of 11 over 11 plus k. There's the answer. Okay, so there you have it. Okay, sure enough. Wow, was it really that easy? Yes, it was. What I'm going to do is I'm going to check the answer just to make sure. What does it mean to check the answer? Take the derivative of this function, see what you get. So I'm going to want to find the derivative of this. Okay, so what's the derivative of this? Well, I'm going to go term by term. So the derivative of this, by the way, it's over 11, which is the same thing as 1/11. Yes, so if you want, you can put the 1 over 11 to the front, okay? Times, so I'm keeping the coefficient. What's the derivative of the variable part? It's a chain rule, so you'll bring down the outside exponent, leave the inside alone, don't touch it, to the power of what? 1 less than that, times, move on and take the derivative of the inside, which is, remember how I keep saying put parentheses around it, okay? And that's why also, because you're not just multiplying it to 12x, you're multiplying it to the whole 12x minus 7, right? And that's the chain rule. Plus, what's the derivative of k? Well, that's 0. Okay, so what happens to the 1 over 11 times 11? It goes away, and that's just left with this. So was this the function whose antiderivative did we have to find? Yes, it was. Okay, so that's how the chain rule backwards works. Again, remember, you must see a product and you must have as one of your factors the derivative of the inside function. Okay, so let's try this again. And we're going to try with the other function which we had. Now I'm going to do this obviously without writing down all the steps. So we want to find the antiderivative of, and we don't need a parenthesis here because, but fine, I wrote it, so I'll just leave it because it's just one term, right? So clearly, okay, so there's that. So what were the parts? The first things first, call the inside function by a u. What's the inside function? Is this exponent. Okay, and again, you must see its derivative. Yes, it's right there with a 6x. What the second part is, well, take its derivative with respect to x. So du dx is what? 6x. Now, next time, I'm not going to even write this. I'm going to multiply both sides by dx, so that's 6x times dx. Next time, we'll just go straight here. Okay. So, I'm going to substitute everything in terms of u's now. So that's going to equal to what? E to the, instead of writing 3x squared plus 5, that's just your u, yes, times 6x dx, right? That's the same thing as just what? Du. Okay. All right, that's it. That's just the u. That's, do you see any x's and u's? No, you just see e to the u du. So what's the antiderivative of e to the u? Well, e to the u, right? It's itself. That's the derivative and the antiderivative are the same backwards. So what do I do? Now my story was again about x's and not u's, so I'm going to go back. So the answer is going to be e to the 3x squared plus 5. So instead of u, I rewrite back what u was, which is 3x squared plus 5. And of course, I should have written the k up here as well. But fine. I'm doing it now. Plus your constant. That's it. So you're welcome to very much try and take the derivative of this and see that you get exactly both these factors. Okay, let's try another one. So let's try something a little bit uglier. Okay, now there's one more little thing that we would have that we might not like. So, I'm going to rewrite this first, maybe. And I'm going to rewrite it, make myself a little bit of room. And I'm going to rewrite it as 5x plus 3 to the negative third exponent. Because again, we might like to see it better as a composition of functions where one of them is a power, right? So we can use the power rule backwards. Okay, so what do you think should be our u? Who should be the inside function? The inside function is clearly 5x plus 3. I know what you're thinking. You're thinking, I don't see its derivative, right? Aren't you telling me that I'm supposed to see its derivative? Where's the 5? Well, it's not there. All right, I give you that. There's no 5. Sure enough, can we add and subtract a number? Can we multiply and divide by a number? Yes. You can't bring in variables because then you're going to have to leave them there. So you can't add and subtract the variable. You could, but it won't be helpful in these problems. But if a coefficient is missing, that's not a big deal. I don't see a 5, no big deal. There's a 5 for you right there. What did I do? Well, I multiplied and divided by 5. Wasn't there a 1 in the front? Sure it was. Yes, so that 1 can be written as 1/5 times 5. Now, do you see a 5? Yes, it's there. Okay, so we'll do some more and you'll see. So what do? I have my inside function. I called it a u. Now I even see its derivative. So what is du? Du is what's the derivative of this with respect to x? It's 5 and then dx. So as I said, instead of writing du over dx and then multiplying it over, it's much faster. Just write du is 5 times the change with respect to x. It's a chain rule, by the way. Okay, so there's that. Do you see a 5 and a dx? Yes. So let's substitute everything. I see the integral. I'm not done with that. I haven't taken the antiderivative yet. The 1/5 is not going to be accounted for, so I have to keep it. But that's okay, because it's just the number. The 5 and the dx, what's the 5 and the dx making? The 5 and the dx is making a du, so I'll write that. What else do I see? I see the 5x plus 3, which I'm going to call by what? U to the negative 3. So I substituted everything. What did I substitute? I substituted the 5x plus 3 with a u. Yes. What else did I substitute? I substituted the 5 dx with a du. Yes, so the 5 dx was a du. And then the only thing that wasn't accounted for was the 1/5. But it's not a big deal because that's fine to have a coefficient. Can I take the antiderivative of this? Sure enough, yes, because I'll just keep the 1/5. So the point is, you can't multiply by an x and divide by an x. Why? Because the 1 over x will still be here. So when you find this antiderivative, as I keep saying, you shouldn't see x's and u's. There should just be one variable. So what's the antiderivative of all this simple integral? Keep the 1/5. The antiderivative of u to the negative 3 is u to the 1 more, divided by that same exponent, plus a k. So if you want, we can make this a little prettier. So 1/5 times 1 over negative 2 is negative 1 over 10. And you can even put the u back on the bottom and give it a positive 2 exponent. You could have simplified it later, but really it's better now because it's less to worry about. So it's negative 1 over 10, and one more time, what was u? U was 5x plus 3. So it's all back to x's as it should be. We just made this substitution to turn this whole big mess into a very, very simple basic, right? Basically, we don't have a composition of two functions anymore. We just have the outside function, right? The inside function is just a variable. That's all we did, right? So we eliminated the inside function by calling it a different name, okay? All right, so I'm going to stop this and we're going to do another video.